Hi, everybody. Let's get started. So today we're going to talk about the planet Venus, which most of you guys probably don't know, but is actually the planet that can ever come closest to Earth. So this is our closest neighbor. Obviously, it has to be at the exact right point of its orbit, and we also have to be the exact right point of its orbit. But Venus is a very close world in many, many ways to the Earth. And we're going to discuss these similarities and differences today. This image is not a true color image of what Venus looks like. This is actually a radar map image of Venus. We're going to discuss today why the best images that we have of the surface in many ways, or what the surface looks like, are actually radar and not actually pictures. So today we're going to be, just as I said, discussing Venus. We're going to discuss various things like the important things about Venus, cratering and surface age of the planet, geology and tectonics, unique surface features that we see on Venus that we don't see on planets like Earth, and its atmospheric evolution and why it's often said to have a runaway greenhouse effect. So, to begin with the key characteristics of Venus, it is named after the Roman goddess of love and beauty and has been well known since antiquity. The reason I say well known since antiquity is, as I said, it can come closer than any other planet. And it is also the brightest thing other than the sun and the moon, natural thing in our sky. So Venus is always either a morning star or an evening star because, of course, it is between us and the sun. And what this means is when it's particularly close to Earth, it is incredibly, incredibly bright. It's like, what's that bright star at sunset? I guarantee you pretty much always that the answer is Venus. Just happens to be in the sky when you're looking. And as a result, it was the goddess of love and beauty because it was the most beautiful star, the most beautiful planet in the sky to the ancient Romans. It happens to be, if you want to see Venus in the morning sky right now. So if you guys, I know you're college students, but if you wake up really early, like 30, 60 minutes before sunrise and it's clear and you look to the east and you'll be like, oh, yeah, what's that bright star? I can tell you right now, it's Venus. So it's very simple to spot. I did look it up. It's going to come back to the evening sky in March or so. So if you don't want to wake up late spring when you look out at sunset and it's after sunset, like a half hour, and you're like, oh, what's that really bright star? You will now know that you're looking at the planet Venus. Venus is incredibly bright because it basically has a huge cloud layer on its surface. It is always cloudy on Venus. That means it is very, very highly reflective, right? It's basically, imagine the clouds on Earth. If we were all cloud covered, it would be even brighter. And that's basically what gives Venus its incredible brightness. Yeah, so if you want to take a look at Venus, you basically have to try to look now next time we don't have a rain cloud planted on top of us in the Pacific Northwest. It is sinking now. As I said, it'll come back in March. Mercury is actually going to make an appearance. I wanted to make a note of that at the end of the month. If you care to wake up in the morning sky, you might see Mercury instead of Venus toward the end of the month. And also, just to give an idea, when I say it's bright, so this is the moon, a crescent moon, and that's Venus. So very bright star, rather planet, morning star, evening star, very easy to spot if you know it's up and you just happen to look. Key characteristics of Venus as a planet. So there's a few things we want to note here. So first of all, its size is pretty comparable to that of Earth. I mean, it's a little bit smaller, a little less mass, 80%, 81% or so, or 82% of the mass of Earth, but it's effectively a planet, you know, rounding errors, comparable to our own. Lighter density, but not a huge amount. Orbital period is very, very different though. So 1 day on Venus, orbital period, it takes 225-ish days to go around the sun, so 1 Venusian year. So that's about 7 months or so. So that's definitely shorter than us, but makes sense. It's also about 70% of the distance between us and the sun. Rotation period, that's what I had to say, is 243 days for 1 day on Venus. So a day on Venus actually lasts longer than a year on Venus. The second thing that's actually crazy about Venus is compared to all the other planets in the solar system, it's actually going backwards in terms of if you're looking at the rotation of the planets. If you say look down from the top down, everything orbits counterclockwise, except Venus goes clockwise. Some people will say, actually, so it's orbital tilt. It makes more sense to think of Venus as this is the North Pole that's spinning around rather than the other way around. People aren't 100% certain why this is, like Venus is upside down. So if you remember when we were discussing planets formed from an initial phase, the dust cloud that collapsed into the protoplanetary disk, that basically means everything should have roughly the same spin in this disk. So some people are like, maybe it has something to do with its interaction with the sun. One theory that I've heard that I think is pretty intriguing is, we know that the moon happened because our moon was created because of a giant impact with some sort of big planetesimal. Imagine something hit Venus in such a way that it basically flipped it over. It's kind of tough to get the orbital dynamics right, but we do think, for example, the planet Uranus spins on its side because of an impact like that. So it's possible, compared to, there's other theories. As I said, nobody really quite understands why, but it's something to keep in mind. It's a very unusual world in terms of how fast it spins or how slowly it spins and the direction it spins compared to pretty much every other planet. Surface conditions of Venus. So if hell is real and is a physical place in our solar system, it is the surface of Venus. First of all, the pressure is 88 times higher than that of what we have on our own planet. So you would basically get crushed within moments if you were to suddenly land on the surface of Venus. The temperature is also insanely hot. It's 750 Kelvin. If you don't know, like Kelvin versus Celsius, it doesn't matter. It's so hot that basically everything will melt. Even lead melts on the surface of Venus. So it is an incredibly hot, and of course, and you can't breathe there, you would die. So like everything is really going against Venus. It's very hot world, very high pressure. Despite that, this might sound crazy, but we do actually have some images from the surface of what it looks like. So these are the Russians basically sent a lot of probes to Venus, finally successfully landed on Venus. And this is what you basically see if you go down there. Should point out that they measured the flux of light in these images, and it's basically the same amount of light as what we have right here, like on a cloudy day on Earth. So it just looks really weird because, as we said, yes. Oh, okay. They basically built something that I'll show you on the next slide. They last like a half hour long and then they die. So yeah, they don't last a very long time, but they do last long enough. Yeah, good question. To get to Venus, you have to do the orbits timed right. It takes a couple months. So it's a couple of months, get down there, and then yeah, your probe lasts maybe a half hour if you're lucky, type thing. We don't do this anymore for a reason, but the thing to point out about this, so Venus, like now we're like, okay, that's silly. Like, why would you send a probe there if the conditions are so terrible? I mean, it's a cloud planet. We couldn't see. There's actually some crazy sci-fi from like the 40s and 50s about like basically the idea that Venus could be some sort of tropical jungle planet where it's always raining and you could have life on the surface, this and that. Because like, okay, we had some ideas. I'm not saying no, like there's some radio astronomy you could do from Earth to measure the temperature of the planet, this and that. But until you actually land there, stick out a thermometer, measure the temperature, you don't really know for sure. So of course, humans, so you're telling me there's a chance, right? So, we're still going to take a look. So this is what the surface looks like. This was the Venera probe 1982, the first color images from the surface of Venus. As I said, doesn't look like much. The other thing I'm going to point out, so here, if you see that little thing, that's actually a lens cap. So the way the Russians built their probes or their landers onto Venus is you would land, there's a lens cap on your camera that would then pop off. The reason this is important to point out is the first time they landed on Venus, they wanted to get a 360 panorama, but they did not because one of those lens caps did not pop off. And then in the case of this particular probe, you'll see that there's a very similar looking thing right here. So this here, you see it here on this side, this was not obscure. You basically have a temperature sensor and a material sensor there, and the second lens cap happened to land and exactly on that. So they measured the composition of their lens cap instead of the planet. So early space travel is hard, guys. Like that's really the important thing here. So exploring Venus, as I said, there were a lot of Russian probes that managed to land on the surface, but you'll see how long, like a lot of efforts have happened over the decades until 1970, 1982, particularly by the Russians to land on Venus. The reason is also it's slightly easier to get to Venus than to Mars, for example, if you just think of like how much fuel it takes. less fuel to go inward versus outward is basically the orbital dynamics reason. So every single time they went, they got less than 12 hours of total data because basically you can see, I mean, maybe you'll last 2 hours if you do a really good job, but that's really, really just such a tough condition to land there. The US has sent probes, but it's mainly been to the atmosphere. We've never tried to land on the surface of Venus. And there have been a lot of orbiters from different countries. The last major Venus mission was actually a Japanese one, just ended. We currently have nothing around Venus. US has not sent anything since the 1990s to Venus, either to orbit or to test the atmosphere. That's actually going to change in the coming years. There's a lot of upcoming missions to Venus. There's some renewed interest in the upper levels of the atmosphere, for example. We'll discuss why that is today. But so, yeah, there has been a lot of efforts to go to Venus and try to understand this planet. Cratering and surface age. So the first thing to say is that there's a lot of similarities to, if you look at Venus versus Mercury and the moon. So I actually have the image there. We have a globe. We have actually globes in this department for like all the main surfaces, which is kind of convenient. I actually was once at a department where they also had a Pluto globe. We unfortunately don't have that one. But the point is, you can kind of look. This is false color mapping, to be clear, to see what exactly there is there. So there's some higher regions. If you see the blue, those are the darker regions. There's some higher regions. We see some craters. We see a lot of different things. Come check out the Venus globe after class if you're interested in checking that guy out. But there's a lot of different things going on. How can we see through the clouds? Radar. So particularly the Magellan spacecraft, which was 1989 to 1994, basically NASA sent a radar mission to go and map the entire surface with radar just to see what exactly there is. I did find a cool video of this, so we're going to watch it if YouTube loads it. Which is basically, so, you know, here you are, you have your, hello, okay, it doesn't want to get bigger, sorry. You have your planet, you can't see it, ground, penetrating radar can go through the clouds. And we can see that there's a lot of different features. There's loops and whirls. This is false color, as I said, so you see there's blue, and then the red is the highest features. So you do have some variation in the terrain. I see a few craters, but not that many, right? Is that fair to say? Seeing head nods? Okay, cool. The black streaks are just where Magellan did not manage to get a radar mapping of the surface. So, yeah, this is basically what Venus looks like. If you were to land a bunch of those Venera probes that only last every 2 hours, that's maybe not the most effective use of time or effort. So, yeah. So here's a question for you guys. Compared to Mercury or the moon, Venus's surface has fewer craters. We just saw in that video. This means its surface is younger or older. That's correct. The surface is, in fact, younger on Venus compared to Mercury and to Mars. So what we know is Mercury, as we discussed last week, is more than 4 billion years old, basically formed and has not had too much activity happening except for some shrinking and craters and things like that. The moon, the highlands are pretty old. The Maria are a little less old, but still pretty old in the grand scheme of things. Venus, on the other hand, is pretty young. The surface features look to be about 300 to 600 million years old, which, okay, that's a long time to us. There were dinosaurs on Earth when, you know, the last of these surface features were created. But if you're thinking of a solar system that's 4.5 billion years old, this is relatively recent. This is in the last 10%-ish of the time. Venus does have craters. Compared to Mercury and the moon, though, Venus's surface has fewer craters that are small craters. And it has a lot more of these complex craters. So complex, multiple, or asymmetric craters. The largest crater is about 93 miles wide, which is slightly larger than the crater that was created when the dinosaurs went extinct. So here's a question that I want you guys to discuss with each other for a few minutes. So first of all, why would we expect Venus to have fewer smaller craters? And why do you think large craters are more likely to be multiple or asymmetric on Venus? Yeah, so like in this left image, if you're looking at the Stein complex, you'll see like 1, 2, 3, 4 craters, and they all look to be comparable in age. So why are they all together? Okay. Did any soul have an answer for number 1? Well, it's not the crater that would burn up, it's the meteor that creates the crater. Yes. So basically, we see shooting stars. Those are meteor, little dust particles burning up in our own atmosphere. Basically, the same thing happens to create craters on Venus. Meteors would burn up even more because that's a much thicker atmosphere, much more pressure. Did anybody have an idea for the second question? So it's not quite disformed. You're close. The meteorites will break up, the bigger ones. So when we saw the video of that Russian meteorite that landed, and I had a piece of a couple weeks ago, you might remember that, there's big, it broke up into a lot of pieces in the atmosphere. You basically have that effect happening because of the Venusian atmosphere, where these bigger chunks of rock will break up because there's so much heat and friction acting on their surfaces. So you could imagine instead of having like one giant crater that's 100 kilometers across, you're going to have smaller craters together that are like, 4 20-kilometer ones. Some of it, of course, is going to break up, so you're going to have smaller things as well. But that's the general story or the general idea of why we think we see these two features on Venus, and also why we don't see them on Mercury and the Moon, which has no atmosphere. So the next thing we're going to talk about is geology and tectonics. So normally when we say the phrase tectonics, we mean plate tectonics, but tectonics can actually mean the surface features, the geology. We still say geology, by the way, for planets that are not the Earth. If you really care about your roots, you might not like that, but too bad. Tectonics just refers to, every single one of our planets in our inner solar system, at least, started the same. Very hot world that then cooled, and then different things ended up happening. So on our own planet, as we know, we have plate tectonics, where the volcanoes tend to follow fault lines, and that's because our crust is broken into tectonic plates. So I'm now going to show you guys, we've mapped where the volcanoes are that we can see on the surface of Venus. And this is what it looks like. So based off of that previous image, do Venus's volcanoes appear to follow fault lines? All right, cool. Yes, it's a random assortment of where these volcanoes are. There's no clear lines. Like I'll show you the image again. Like think of the ring of fire around the Pacific Ocean. Compared to that, there's no equivalent here. We think the reason for this is plate tectonics actually needs you to have some liquid water on the surface to exist. Basically, the plates that we have, the reason volcanoes exist is they're grinding past each other, they're sliding past each other, things like that. If you don't have water to lubricate the plates, then they actually don't really exist and they kind of dry up and they don't move. So we think that's actually what's happened to the volcanoes on Venus, is because you have no plate tectonics, they just randomly show up where they show up, and that's what you got. So yes, this means that there's no evidence of plate boundaries like we have on our own planet. And we do think that there is mantle convection. The reason is it is the size of Earth. Earth, of course, has cooled a bit over time. Venus has also cooled over time, but we don't think that it has cooled much more than the Earth. But any convection that occurs in the crust is closed. I will also point out that Venus actually has no intrinsic magnetic field like we have or even Mercury has. There's jury is still out on how you could have, volcanoes and not have a liquid core that then gives you a magnetic field. So there's some sort of convection happening inside Venus, but we just don't understand exactly how it's different and how it's similar in some ways compared to our own planet. So a better way to describe the tectonic activity on Venus is actually blob tectonics. So Venus's surface features come from basically rising and receding lava, flood volcanism, or hotspots. So you get some features that we don't see on Earth, but you see on Venus. So you see, for example, here, some ridges and cracks. So this is buckled ground, which keeps being stretched and compressed because of activity around it, but it never moves. It never slides somewhere else like it does on Earth. It just keeps doing this. You also get coronae, so crown-shaped concentric cracks, which are thought to do if there's some sort of activity underneath, but it hasn't quite pushed through. And lava domes. I mean, to be fair, we do have some lava domes on Earth. You can go out, east toward Bend and see quite a few of them. But we do see them. They're kind of different on Venus. They'll be very pancake-shaped wrinkled domes. So you probably had some hotspots break out, but then not last very long. And they have a slightly different feature compared to what we see on our own planet. As a final note, the thing about that's actually maybe the most interesting thing about activity on Venus is we actually now think that there's present day volcanic activity on Venus. So this came out a couple years ago in 2020. And basically there was a reanalysis of some of that 1990s data from Magellan, and they found evidence of active volcanism occurring on the planet. So if 1990 there was still some volcanism happening, then it's probably there today. It's just really hard to see when you have a cloud planet and you're never going there with any space missions or anything like that. So this is, as I said, been kind of a new idea or a new observation, reanalysis. And the general idea is you have some sort of oxides there that are not obscured and have to be recently replenished on the surface, or else it's tough to explain why you have these materials there. They wouldn't be there unless, in the recent months or years they were placed there. So these are hopefully things that will be addressed in coming missions, or at least we'll understand a bit more. As I said, there's a lot of questions about the tectonics of Venus that we just don't understand right now, which is, as a scientist, I personally think is a pretty cool place to be. The atmosphere of Venus. So the atmosphere of Venus is it's much higher pressure. So that means there's a lot of different characteristics compared to our own. I mean, it's the planet the same size as Earth. How can the pressure be 80 times higher on the surface, right? So we're going to think about this in terms of first the primary and secondary atmospheres of Venus. And the first thing to note is that they're pretty much the same for Mars, Venus, and Earth at the very beginning. So the first atmosphere is just hydrogen and helium, and basically got lost to space very, very early on in the planetary formation process. Then you have a secondary atmosphere, which is primarily water, and then carbon dioxide, sulfur dioxide, other things. This would have been formed from volcanism, and it would have evolved and changed over time. So we've been discussing a lot recently about escape velocities for gases. So Venus has an escape velocity of 10.4 kilometers per second. I'm giving you a bunch of gases. And which of these secondary atmosphere gases would be expected to escape Venus and be lost into space? Where this is the reminder of what you need to think about, multiply by 6. Okay, yes, I see consensus. None of these. They're all there still today. Well, they were originally there. We'll discuss what happened to everything. So if we look at the current atmosphere of these different planets, the current atmosphere for Venus is primarily carbon dioxide and a little bit of other things, hardly any water today. So it's not because of the escape velocity that we lost the water. We're going to discuss why that is. So we discussed the greenhouse effect when we were discussing our planet Earth and how there is a greenhouse effect on Earth and how humans are, contributing to the current climate crisis due to the greenhouse effect and carbon dioxide. Venus, however, is basically what's called a runaway greenhouse effect. And this has to do with the fact that it's closer to the sun, much closer to the sun than the Earth. And this really does matter in terms of the planetary atmosphere and how it evolves. So to remind you, you have incoming sunlight. Some of that sunlight is reflected, but some of that sunlight comes down onto the surface. If you have oceans, then you're going to have some of the water absorb that carbon dioxide. And then some of that water is going to evaporate. This depends on the temperature of the planet. This can change if the temperature of your planet increases. This cycle will also change. And then you're also going to have your atmospheric CO2 concentration as a result change. So you're going to have infrared light because the planet is going to have some heat emitted from the surface. Some of that's going to be re-emitted. Some of that is just going to plain old escape. So Venus is basically sufficiently strongly heated by the sun that water vapor can rise much higher in the atmosphere than it can on Earth. And that's just because you're closer to the sun, you have a higher solar flux at that distance to the sun. What ends up happening then is the hydrogen and oxygen in water can be split by ultraviolet light. And then the hydrogen basically escapes immediately, kind of like it did for that primary atmosphere. And then the oxygen oxidizes very quickly into the rocks around and things like that. This means that also then once you have no water or less and less water to absorb carbon dioxide on the planet, then you're going to have what's called a runaway greenhouse effect. And that's also then why, you're going to have a stagnant planet that's not having plate tectonics. You're going to have a lot of carbon dioxide, basically no water. So to be completely clear, we think when Venus first formed, its secondary atmosphere and its conditions were very comparable to that of Earth. It probably had water on its surface like we did, but probably within the very beginning, couple 100 million years maximum, everything changed quite a bit. So the water disassociated because of that, as what you say, because of that UV radiation. So just in case it's not clear from the verbal description, water has, one oxygen atom, two hydrogen atoms, shine some UV light, then one of those hydrogen atoms is going to fly away, maybe both of them. Basically, once you get high up enough in an atmosphere, this is what's going to happen. So the water is basically pretty much gone now from the surface of Venus as a result of this runaway greenhouse effect. The carbon dioxide, though, survived. It's doing pretty darn well. It makes up pretty much the entire atmosphere on the planet of Venus. Sulfur dioxide has stuck around. So there's sulfuric acid rain on Venus. It doesn't quite make it to the surface. So, it's probably the most hellish surface, but, you have to get through a sulfuric acid rain to get to it as well. So, don't go to Venus, guys. The nitrogen that did survive, because nitrogen just kind of hangs out, and survived-ish. There's a little bit less. And then otherwise, there's basically some noble gases that have hung around as well. So the final thing here, we can compare then the atmospheric structure between Earth and Venus. So this is if we think of the temperature of both planets and we think of the height and how the two relate to each other. So we have our troposphere, we have our water clouds, so the clouds you see in the sky, ozone, the meteors that you see, the shooting stars, are pretty high up. They're almost 100 kilometers up. 100 kilometers is traditionally defined as the boundary between Earth and space. There's still a little atmosphere up there, but not an awful lot. Venus, on the other hand, is pretty different. So you have up to 20 kilometers, you have sulfuric acid clouds over a 30-kilometer troposphere. So it's not a great place to be. As I said, the pressure is very, very high if you're going down to this bottom part of the planet. Fun fact, though, so this is just kind of an interesting thing about the atmosphere. Once you get above this 50-kilometer line for Venus, it actually turns out to be not that bad. So once you get to about 50 kilometers, this is the air pressure on Venus by altitude from the planet. So kilometers from the surface, air pressure in bars, as I said, you're like 80 times higher than Earth pressure. Once you get over 50 kilometers, though, you're basically at the same pressure as you have on Earth. Also, you still have enough atmosphere above you to protect you from a lot of the effects of the atmosphere, things like that. And the gravity is actually pretty comparable to that on Earth. I mean, the planet is about 80% the size of our own. So it's world for world, the gravity alone is better than it is on, say, Mars. So, I mean, I said that people speculated before we could see the surface of the planet, what lived on the surface. There's actually some interesting ideas now that maybe someday we could have cloud cities in the atmosphere of Venus. So you'd never really be able to land, but you would kind of have like blimps, or maybe like in Star Wars, they have the cloud cities high above, like that Lando Calrissian lives on, things like that. So this is like NASA's actually done mock-ups. I don't think it's that NASA is serious, but more that it's fun to think about. And then they put challenges out to engineering students to design. How could you design a city that would float around, on a giant blimp above those sulfuric acid clouds, like if astronauts wanted to someday study the planet of Venus? So there's definitely a lot of interesting features here.